currently a deputy head and a senior researcher of the Department of Embedded Intelligence from DFKI. He's also on the steering committee and TPC co-chair of EastWeek. That's one of the top conferences on wearable computing. His major research interests include the crossover of hardware and machine learning, sensor-based human activity recognition, multimodal information fusion, biomedical engineering, sustainable machine learning, and electronics, smart textile. He leads the research of several EU and Germany national funded projects in this direction, including Sustain ML, Simple Skin, Vid Gen Sense, Social Wear, Health Sense, etc. He has a diverse education background from control, instrument, navigation, system on chip, sensing on the hardware aspect to machine learning and AI on the software aspect. So I met Dr. Zhou in UbiCon last year. I was really impressed by the work, and he seems to be all over the place in the conference. He has several papers actually presented. So I think it will be a great opportunity for SMAP trainee to have the opportunity to interact with Dr. Zhou. All right, without further ado, the podium is yours.
Thank you, Ron, for the introduction. It's great to see you again, and I'm happy to be here to present some of our work in these directions. So maybe first about DFKI. It's the German Research Center for Artificial Intelligence. It is one of the biggest public nonprofit AI research centers. So we are located all over Germany, and our department is located in Kaiserslautern, where Frankfurt will be somewhere here near Darmstadt. Yeah. Actually, Ron did a great job introducing. I don't need to repeat anything on this page, so we can go right into the topics. So today I want to introduce. So I changed a little bit in the title. I put ubiquitous next to wearable, since Ron told me this seminar is interested in assistive living for aging community. So I added ubiquitous to the topics. So first I will show some example applications, and then go into the some direction of the simulating sensor data from vision, from specifically pose, and then something about multimodal sensor fusion, and embedded how to deploy machine learning models on the edge, on the hardware. So I hope there is a bit of software, a bit of application, bit of hardware. So maybe I hope there are enough interest from different students. So the basic idea of wearable and ubiquitous activity recognition is when we have different physical activities, we will cause the reality change. Will cause physical changes in the reality, and these changes can be picked up by various kind of sensors. And usually, these sensors are not originally designed to detect these activities. They are just designed to pick up some changes in the physical parameters. But certain activities might cast very specific characteristics in the sensor signal. And human activity recognition is essentially the field try to infer to these physical activities from the pattern characteristics. So, for example, the most well-known sensors are IMU, inertial measurement units. People use it widely for motion sensors, but they were initially invented, designed to for controlling, for especially for rocket controlling, to measure the acceleration, or for inertial navigation. And then they were made very small to put in the cars for the collision detection, for the airbag trigger. And then they were put into smartphones for gaming, actually, for steering wheel, for driving games. But people realize these sensors can be used to detect a lot of physical activities. So now there's a broad field for using IMU for detecting human activities. And there are many other sensing modalities that we can use to infer to the actual physical activities. So I think we will go through some examples, some not so well-known examples. For example, bioimpedance. Bioimpedance, likewise, it's usually used in the medical field. Maybe you have body composition meters, and they use bioimpedance because the fat and muscle and the skeletal muscle composition will change the human body's bioimpedance. But maybe you remember when you measure the bioimpedance, when you use these smart scales, for example, you need to keep steady because the bioimpedance also changes with the motion. So usually these motion are regarded as artifacts. And so the user, when we want to use bioimpedance, we recommend the people to be steady. But these dynamic patterns, we can actually use that to infer to the physical activities. We just need to measure the bioimpedance fast enough. And now we can measure the bioimpedance pretty fast, around I think 30 hertz. And we can see the dynamic changes. For example, in this case, we have two bioimpedance electrodes on the arm, on the wrist. So at idle, we will measure this bioimpedance through the arm to the shoulders, to the collarbones, and to the other arm. So that's the idle bioimpedance. But once, remember, bioimpedance measures the conductivity. So once you have a metal knife and fork, and when you touch the food, for example, when you're eating, and the food is also conductive most of the time, and then you will form a new circuit around the food. And then this happens so that we have a different characteristics of the impedance drop because it suddenly becomes more conductive. And it goes the same as when you put the food into your mouth, you will form another short circuit through the mouth. Then there's another smaller drop in the impedance. So we can use these dips. They all look very different dips based on what the actual action is. So we can use these certain patterns to detect what kind of eating activity this person is doing. We can also use, with a similar principle, we can also use the bioimpedance to detect the face to hand-to-face gesture. This was a work we just presented this week in Augmented Humans. It's the same principle when you touch the face. So, for example, when you have your hand hover the face, there's or when you really touch the face, you cannot really detect it through the camera because the face contact is blocked by the hand through the camera. But with the bioimpedance, we can detect when you touch the face, and actually the surface, the how much you're touching the face, we can also use this to detect. Yeah, this is just the result is pretty good. And another pretty interesting example for sports, we can use that to detect sport activities. So for example, we put the same electrode on each arm, and when we move the body, even though we're not forming new circuit, but when you move the body, the impedance also changes slightly because because what impedance is how is basically the volume divided by the cross section in ideal cylinder way, but the human body is a 3D volume that changes all the time based on your actions. So this will also cause a very characteristic changes in the bioimpedance signal. So we can use this to detect the physical exercises. And we also have another, in the same paper that we presented on PairCom this year, we also have another use case that we attach electrodes on the calves. So we can use that to detect the leg activities. Yeah. So that was about the bioimpedance. So again, the bioimpedance was recommended to stay idle when you want to use it for body composition measurement. But if we can measure the bioimpedance fast enough, dynamic enough, we can use that to detect those artifacts. These are maybe artifacts for one use case, but they might be very useful for the human activities. And then another example is capacitive sensing. This was one of the work I presented on UVConf. So capacitor, normally we have touch screens are capacitor, touchpads are capacitors. So capacitors, the capacitance is changed by several factors. So one thing is the dielectric in the between the two pads. And if you have a parallel capacitor, imagine, and then you move the one plate away from another, then this capacitance will change. And we can use this characteristic to put two plates on the body and to use this to measure the change between the body. We can also have one plate attached to a virtual ground, which is being used in this application. Then the capacitor will be more sensitive because the field, the electric field permeates in the whole sphere of the space without really another plate to go. So then this is more sensitive to the human motion. So normally the virtual ground capacitor is not used because it's too prone to interference, but we're actually using this interference to detect those human activities. And in this case, we positioned different capacitor plates on the upper body, and we observed that. So first, this was before this paper was another paper to detect the gestures, to classify the gestures, but we realized these patterns they repeat very repetitively with with actual pose. So then we say, okay, we can use this to reconstruct the pose. So this is basically a capacitance poser. So can we put in all possible sensors available to see what we can detect? Like make an ultimate sensor, because the way the human perceive the environment, perceive the activities, is through multiple senses. We don't rely purely on one sense. We usually have different senses together. So this is one work that we put. For example, the sensing modalities are not in here. We have inertial measurement units, thermal cameras, air pressure sensors, and optical light sensors, and the UV sensors. So we put all of these sensors on a single node in front of the person, and we try to see what we can detect when people are doing cooking activities, which is quite relevant to this elderly home care, I think. Yeah, so the result is pretty good. I will further follow up on this later. And we also put many sensors in the environment. So apart from the body trackers, we also have motion trackers on the chair. So your posture, or your activity, can also be detected from the way the chair moves. And we also have eye trackers, and we also log the screen of the screen and the user input, and we let people play League of Legends. So this was an example that we want to see if we can use multiple sensors to detect those social interactions, or rather teamwork. So this study was designed so that we try to find an easier way to do the experiment, because teamwork is a very complex, very sophisticated topic, but we also want to have stress in the teamwork. So then we thought, okay, actually esports is the most stressful one of the most stressful tasks, and without people needing to move too much. So it's easier for us to install sensors, essentially. And we can detect, we basically saw that there's a synergy from the physical sensors, that when some certain events happens across the team, we see the same type of sensor change across different users across the team. And we can also use these sensors to detect, because it's an esports, so you win or you fail or you lose. We can use this to forecast whether the team will win or lose in the next few couple of seconds. Of course, as the window grows longer, the forecast goes more to the chance level, which makes sense. But for example, we can say whether in the next 10 seconds, if the team as they are now they're going to win or lose the next encounter. So this was pretty interesting. That was not expected before we designed the experiment. And another work is not from us, is from Carnegie Mellon, I think. This is rather a smart home super sensor. So they have this USB plug combined with all of these embedded sensors. And we can see, and the position across different rooms in a home. And I can see that at different actions will cause significant changes in different sensors. For example, with the kettle, we see the vibration from the acceleration, and of course the microphone. Or with the EMI, we see the microwave, and we see when you open or close the door of the microwave, because the EMI escapes the Faraday cage of the microwave door. Yeah. And when the microwave is running, there is actually no radiation. So which is quite, it was quite interesting for me to see that there is no radiation even when the microwave is running. If the door, of course, the door needs to stay closed. And then I want to go to these details about simulating sensors signal. So when we talk about simulating sensor signal, we kind of need to select one modality. So I want to start with IMU because people are most used to IMU, and it has been so widely studied across different sports activities and human activities. So just some hardware background, because in my bachelor I designed IMUs. So the IMU, they measure the acceleration and rotation, and if you put in a Hall sensor, you also measure your relative orientation to the magnetic north. So the IMU, they do not really give you the motion path. They rather give you the acceleration. And there's a relationship between the acceleration and the path through the double integration. But because IMUs, they are not ideal, so there is saturation. So for example, you see this is the proof mass with the spring system. Imagine what happens when this collides with the other, when the orange collides with the green. That's when the sensor saturates, and it actually happens in many use cases. For example, I saw a study putting IMU on hand and to detect volleyball, and the motion of the spiking of the volleyball essentially saturates the IMU sensor. It exceeds several tens of Gs. Yeah, so we cannot really use IMU directly to inverse to the trajectory to detect activity. We rely on the patterns in the acceleration and rotation to infer to the actual activities. So, but the other way around, we can simulate IMU signal. So in simulation, we don't care if it's saturated. We just need a certain amount of data, so that we can use that to train the model. So the biggest challenge in human activity recognition is that there's not enough well annotated actual physical sensor data, unlike the cases of vision or language, because the nature of sensor-based activity recognition is the sensors are heterogeneous. You can have all different kind of sensors, and the sensors can be positioned at different locations. And so when you have the same sensor positioned on different location, they will have this different characteristic with the same activity. And also, it's not easy to interpolate sensor data, because when you see sensor data, you see just these waveforms. Even for experts, we do not really know what they really stand for. We have to look at the synchronized experiment video, which makes sense because motion, vision and language, they go in together, because the language was invented to express what we see, but sensor does not have that benefit in this loop. So one example in this direction is that we can simulate sensor data from video. We need to have the position of the sensor and the trajectory of the virtual sensor, and then we can use this forward kinematics to derive the acceleration and orientation. So this is a work from YouTube. So essentially, with the YouTube videos we already have annotation, because usually there are captionings coming with the YouTube videos. And then we can use the vision models to extract the 2D pose. And with the temporal domain, we can also extract the 3D pose. And then with the 3D pose, we can use forward kinematics to derive IMU signal. And with some post-processing, we can have a virtual IMU dataset. The benefit is that we don't really need to conduct experiments to have this virtual dataset. Because conducting experiment with sensors, I think, as your lab will also know, is one of the most costly parts of a study. And then we can use this virtual dataset to pre-train a machine learning model, and then maybe fine-tune on a real dataset or do zero shot on the real dataset, and to see whether we can improve the model's performance. And this is another example. With the same direction from video, we extract pose. There's some nuance differences. I think we don't need to mention that. So like feature guided signal reconstruction. So we just saw from video to pose to IMU, but we actually don't need videos because we needed a video for the pose. But if we can directly use the pose, we can also simulate synthesized sensor data. So then there are works on using pose, so text to pose generation. So we can generate pose from text because in the motion capture discipline, there are many works in this direction. In animation, for example, maybe you saw some NVIDIA demos that you write some text and then you see an avatar being animated. So it's the same type of model. So it's text to motion models. So, but text to motion models, they kind of need very specific instructions. And so then this work is using text. Maybe we have jumping, and then we ask another language model to elaborate this jumping. So to explain what jumping is, or write a scene that is detailed enough to describe jumping, and then this more detailed sentence can be fed to the text to motion generation models. And then we'll have a sequence of poses, and then through the kinematics, we can derive the virtual simulation data, simulated IMU data, without any video, without any actual source of motion. But there are some nuances. So what we saw so far are generating the IMU signal from the joint, from the pose joint. But that is not really the sensor position. The pose joint is anatomically inside your body, it's inside the bone. It's not really the same as if you put a sensor on the surface of the body. So then there are some nuances that I want to touch in details. So that was the joint system. So IMU-tube or IMU-GPT are in the joint. Or there are newer works, so IMU-poser, they use the surface, or chromosome, actually from Rome, use the surface mesh. So these leverage the volumetric pose, SMPL formats, for example. Or we can really simulate an accessory on the body. So through soft body simulation as the appendage on top of the body mesh. So these are already work published, and we're actually going to finalizing one paper in this direction, hopefully this week or so. Yeah, just some more graphical explanations. For example, the IMU poser, it was a paper on Kai. So he used the AMAS, which is a large motion capture database. He used that database as the motion seed, and then they put the virtual sensor on the vertex of the surface of the human body, and then simulated a lot of virtual sensor data to train an IMU poser, to train a pose reconstruction model from the IMU, so that he can use this model to do a avatar animation from sensors, from smartwatch and smartphone and IMU enabled headphone. But in that work, because the vertex on the surface does not have orientation, so his orientation came from came from the 24 joint skeleton joint again, so which is not really how it's supposed to be. In this other chromosome paper from Professor Zhang, actually, I saw you selected three vertices, which would define the orientation, which is actually a huge improvement on top of everything that we saw, which will give you both the orientation and acceleration in a more realistic way compared to directly using the joint system. Okay, so with IMU and vision, we can also devise cross-modal contrastive learning methods. So maybe you know CLIP, which is a language vision pre-training. We can so CLIP essentially has a vision encoder, language encoder, and they try to align them in the sample so that with the finalized model, you can use that for image retrieval or image annotation. And there is also IMU clip, so it's together with the sensor. So you have a sensor encoder and a vision and text encoder, and they're aligned pairwise. So they still have to train it pairwise in the contrastive space, so in the joint representation. But the result would be that they can use this for sensor data retrieval. One thing, they can also use this IMU encoder as and together with the text encoder as a zero-shot classification method, which is quite interesting. However, the limitation was that this was an egocentric data set. It was essentially a GoPro on the helmet. So the IMU was only on the head. That you can only detect so much with your whole body moving. If you have something that only involves moving your hand, then that will not help in this case. But that was a limitation of the data set. It's not really a limitation of the method per se, but we believe this method can have some more potential if we have better curated, formulated data set. And another work from us about further synthesizing data is we thought through diffusion. So diffusion is a method that you may well know for the deep fakes, for example, or style transfers, or DALL-E is a diffusion model, for example. So the way diffusion works is you have an original input, and then you add noise to it, and then you denoise, and then you will have a new output that is similar to the input, but is different from the input. So this is the way diffusion works. But we can guide the diffusion process by how we add the noise. So normally we add a Gaussian noise, but we can add for example, feature guided noises. Then this diffusion is feature guided, and is more grounded than the simple diffusion and than basic diffusion. So maybe we just look at some data. So we use the diffusion. We use diffusion to synthesize data and use that data to pre-train machine learning model to detect activity, and we found out that outperforms the activity with for example, oversampling methods and or GAN methods. Okay. So that was about the IMU, simulating IMU data. I want to also introduce another sensing modality that is the surface planar pressure. So imagine the pressure matrix. So every centimeter we can measure the ground pressure. So this is what they call SmartMat. This was one of the work I presented on the Pericom as well. Ubicom as well. So this was a study that we want to see whether we can detect the quality of execution in sports. So you see, this is me doing different types of crunches of different endpoints. So one is from lower to medium angle to high angle. So it's different ranges of motion. So we have this experiment of categories of exercises with detailed subclasses, which would represent different levels of quality of execution, and we want to use this to detect the quantify the execution quality. So this was the result of the quantity of execution, quality of execution. So well, if you see the recall F1 68% is pretty maybe not so high, but if you imagine the 47 classes, the chance level is 1/47, so that's pretty significantly above the way above the chance level. So then we thought, okay, maybe we can simulate this data too, because ground pressure is pretty easy to simulate once you have a volumetric pose. So we just need the volumetric body, and we need to simulate the gravity, and then we have a ground surface that we can do collision. And we just need to register which point is the collision between the ground and the volumetric soft body. So this was the work of us on simulating the ground pressure of a human doing different yoga activities. So we have people coming to our lab doing yoga, and we capture their pose through a video. Then we rig the skeleton with the volumetric body, and then do a ground collision, and through but we realized that this is the naive ground collision. So it's very artificial. We found out, because that's the nature of simulation, because it's very ideal. So there will be like a highly concentrated pressure points or very small points that doesn't really happen in reality, because for example, the mat itself is a foamy surface. It's not really a so there's not we cannot really simulate every aspect in the reality. So that we added a post-processing neural network, and so this was trained with the input of the ground collision simulated data, and the output with the synchronized real collected sensor data. So we use this to as a post processor, for example, as a post processor for the ground collision, and then this is the sorry. So this was the baseline, that only the ground collision, and this was the real the one that represents the most to reality with the post-processing model. So the red dots represents the discrepancies between the ground truth and the simulated output. And then once we have the simulation, once we are in the virtual world, we can change the body shapes. So this gives us more advantage, because we can have different bigger body, smaller body. This was actually one of the questions in my own PhD defense, and how can we make it easier so that we can, because people of different body lay on the ground, they have a complete different shape. So we can easily swap this by changing the body in the simulation pipeline. And then again, we want to completely get rid of the vision. So the vision was the stepping stone for us to get there, but we can completely get rid of the vision again with only language to pose. So it's the similar idea. We input a simple word, a simple class, and then we ask the GPT to elaborate this class into a more detailed language, and use that language to generate motion through text to motion. And then through the whole simulation pipeline, we can have a purely simulated data without any seeding motion, for example. We can use that simulated data to fine-tune, to pre-train or fine-tune, on a model that's then use the model to detect the real to recognize the activity on the real data. So for example, on the right is trained on real and simulated data. It outperforms trained only on the real data. But what the ideal way would be, we have zero shot. That means if we train only on synthetic data, and then did test on the real data, um, um, but the basic one doesn't really work so well. but we found out we add enough variations in this style transfer. This is simulated data. We added swapping the body types. So we switch different body types of the same motion, and then they can already outperform on real data. So this is essentially fully trained on simulated data and zero shot on real data, and this already outperforms the real data. Okay, and the last point, no, the second last point, how do we use this different data? How do we use different data to improve machine learning? So this goes a bit in the deep learning direction, but not really. We're not going to talk about model architectures. We're going to talk about some learning paradigms. So we can have the same we can have the same data and the model, but with different results if we change the learning paradigm. For example, in human activity, we have this problem of different users and different user, they perform the same activity in different ways, but we want to have a model that is user independent. So we want to have a model that can be used to detect the same activity from different users, which is easier said than done. So we can leverage this nature in the activity recognition. So we can have a adversarial learning. So we can have different user as the adversary. So we can have a discriminator to discriminate whether this data come from user 1 or 2 or 3, at the same time detecting the activity. And we found out that this improves dramatically the user independence. So through the adversarial learning, it's the same data set. We just need to feed the information of the user discriminator, and then the model is the same. The eventual model for the human activity recognition is the same. It's just we added the adversarial learning in the middle during the training process. And another add-on on this is we added self-knowledge distillation. So knowledge distillation is a way that we have a teacher model, pre-trained teacher model, and we use that teacher model to regulate the student model. So usually the student model is a smaller model, but it's not always the case. We found out that we can have the same, exactly the same architecture of the teacher and student with the teacher pre-trained. It will still improve the student model's activity performance, so that we added the adversarial user detection together with the pre-trained self-knowledge distillation, and we basically achieved refreshed state of the art in the benchmarks of the activity recognition data sets. So this was a result of opportunity, but in the paper. In this paper, you can see that through these two mechanisms, the method outperforms other methods in basically all of the activity recognition benchmark data sets, like PubMap and Opportunity and MMFit, for example. Okay, so another use case, not really use case, another way of tuning the learning paradigm is we may have different sensors on different locations. And for example, we may be this one on the hand, one on the foot, and we want to detect motion on the hand through the sensor on the foot. That's usually, if you think about that, maybe that's impossible because your hand is moving, your foot is not moving. But a little bit of that motion will be propagated to the foot. So because your foot is not completely idle, because your when you're doing a lifting, your center of mass is shifting, and your body needs to counterbalance that shifting of the center of mass, and that counterbalance happens on the ground. So there is a little bit wiggling happening in that foot IMU, but it's the signal is so small compared to the other activities in the data set. But remember, in the machine learning, in the normal training process, you have different classes and they are treated with the same loss function. So these very small signals will be buried by the more significant signals. But if you have another source data that is synchronized with your target sensor, that is right at the motion position where this negligible motion is happening, then we can use that to amplify this. So this is we can use this as a contrastive learning. So for example, for each activity, we learn from the best modality and then condense all of that on the target modality. It's not really pulling a rabbit out of a hat. It's really just using different magnitudes of sensor to concentrate on a single target modality. So this is what we call learning from the best modality. And it was a paper on 2022 EASWIC. So what we need is basically essentially encoder for each source modality, each source sensor, and we have a translation layer so that they can be interchangeable. And then we will have a contrastive loss between the two modalities after the translation layer. Then with this translation layer, we select the target data. We have the source data. When we put two modalities latent vector together in the classification process. And in the end, we only use the target encoder and classifier. So we don't need the source knowledge encoder anymore for the final test. And I think maybe which one is the most interesting one to see? Okay. Actually, each you can see the improvement is each of the improvement is much better than the baseline. So the baseline with the different three different sensor locations, and for example, walking from the hand, walking from the hand, with the source mode with the source of the hand, is already way better. I will maybe okay. So I want to continue on that on the bioimpedance. So this was actually part of the bioimpedance work that I show with the exercise, with the physical exercise. Because bioimpedance is a little bit difficult to deploy, we need to put a sticker on the body, but we found out we can use that to improve IMU sensor because it's easier to wear IMU in the wild, but in the training process, we can gather a corpus of data enhanced by bioimpedance data of the sports exercises and use the similar contrastive learning process to enhance a target modality of only the IMU sensor. So again, eventually only the IMU will be used, but the bioimpedance through this contrastive pre-training, through contrastive training process, we enhance the IMU on certain activities. And the last part will be I want to go into sensor fusion. So we want to use maybe all of the sensors together because even with the contrastive learning, we use one modality to enhance the other modality is still not as good as if the other modality is also there in the system. So that so sensor fusion, people usually categorize as a data fusion or feature fusion or ensembled fusion. It's just a matter of where we concatenate the information together. So either at the data source or after the feature encoders, and the ensembled classifier will be concatenating after different classifiers. A nuance for sensor-based human activity is different sensor have different sampling rate, and different sensor has their own optimal sampling rate. So maybe for IMU, we prefer a faster sampling rate, but for example, gas sensor, for air pressure sensor has a lower sampling rate, or for temperature sensor, it has a different characteristic of the sampling rate. So we added the learnable layers in this fusion sensor fusion architecture, and we try to optimize for the best sampling rate. So this was another direction that we have evaluated. This was presented on a AAA workshop last month, or when is AAA 2 months ago. And deploying the machine learning on edge devices, I hope some people will find this interesting, because this is one of the, if we say we do human active recognition, we do a lot of studies with the benchmark data sets, but eventually we want to, if we want to use it in real life, we need to have them running on the embedded devices, because we cannot really stream 100 hertz IMU data constantly to a server to occupy the data streaming bandwidth. So we can deploy trained machine learning model on microcontrollers. So there are several libraries already existing for them. So for example, TensorFlow Lite or PyTorch also has a new library that I don't know, I forgot the name of it. But basically the idea is you train the model on a GPU, and the model is nothing but layer descriptions. So we just need to translate the layer descriptions and embed it, deploy it on the microcontroller. But the difference is the knowledge that you will learn from practice is that we need really small models. So that's why maybe at the beginning, I skipped that slide. We have 3 sustainable AI projects. They are focusing on small models, because for the embedded devices, we really need to have really small models. To have a small model is one thing, and how we trigger the model is another. So we can have, for example, I don't know if this is already here. For example, we can have a thresholding detection first for a motion threshold. Once it exceeds a threshold, we trigger a machine learning model to detect the activities. We can also have hierarchies, for example, a binary model to say whether this is a gesture or not, a much smaller binary model, and then a more detailed model to detect what kind of gesture that is. So this will essentially save a lot of energy on the long run. So which is essentially good for wearable, because wearable usually need to run on battery. Yeah, and the next step will be deploying machine learning models on FPGAs. So FPGAs or Verilog, it's a different way of thinking. So for Python, for example, for Python written models, we can directly translate that, because the TensorFlow Lite has a library for you to directly convert your model to it. But if you want to do it on FPGA, so the FPGA has the benefit that FPGA is field programmable gate arrays. So it's runs in parallel. It is essentially before you make a chip, you should simulate your circuit on FPGA before deploying to a chip. So that if we talk about RISC-V, for example, or accelerators, specific accelerators, we need to have these algorithms written in the RTL level. So RTL level, so to deploy on FPGA to test them. So then you can see this is a way different. So this is a convolution layer, for example. It's a way different than what we saw with the Python or mathematical equations. But it is the how the mathematical equation is expressed on the circuit level, on the register level. And this is a dense layer, for example. And probably the dense layer, since dense layer is not so much different from convolution layer, the difference is a convolution layer has this kernel of a convolution. We can see that we can maybe tell where is the convolution happening. I think this convolution counter, this convolution counter is what controls that convolution layer essentially. I can skip the animations. And yeah, this was a work from us for, we want to have different sensors from end to end, so different sensors, sensor interface, so data acquisition front end combined with the machine learning model inference together in the FPGA, so you can have everything in one single chip. One nuance about FPGA is we can arbitrarily quantize the model. So quantization is something that you will touch on when you start to use embedded devices. So we train the model maybe on graphic cards on GPUs with FP32 or FP64. What it means is they are floating point 32, but embedded devices usually don't have that. Embedded devices has maybe the integer 8 or integer 16, integer 32. That's what's usual on the microcontrollers. Microcontroller also has the floating point, but they are also usually much shorter. So maybe FP16 or FP8, so much lower precision. But on the register level, it's really everything runs on integers. So we need to quantize the model to the integer precisions. The nice thing about FPGA is because you are implementing the circuit, so each bit is a register, so we can have arbitrary precisions. Unlike on a microcontroller, you still have defined precisions, so 8, 16, 32. So we can observe this accuracy drop. So what this curve means is our quantized precision, our quantized precision accuracy divided by the full precision accuracy of the model inference. So we can see that at 16-bit, it's up to 10-bit. It performs the same as what it runs on FP32 on the GPU. But once we quantize it even more aggressively, the model will start to lose the accuracy. So what is essentially in the sustainable machine learning or sustainable embedded machine learning is finding the sweet spot that has the best performance and efficiency. Maybe some other nuance. Maybe it's interesting for you to see. I don't know. For me, it's no. For me, it's normal. But for people outside this domain, it's actually sometimes it's interesting to see. So even for FPGA, they have certain accelerators. So I said we can quantize them to arbitrary bits, but the difference, for example, from 8-bit to 9-bit, then there is a 8-bit with accelerator on FPGA. So if you use 9-bit, then it will need to initiate two of those accelerators. So you see something interesting. This resource doubles once we just jump 2 bits. So that's why it doubles, because it initiates another array of accelerators. So even for FPGAs, there are still certain hardware accelerators, but it helps us to run everything faster. So maybe again, why did we do this on FPGAs? Another thing is about timing. So this was the timing plot of the same use case of the same dataset, sensor dataset. So these different colors here are the reading sensor operations. So on the sequential on a microcontroller, we need to read the sensors. It takes 1 second or something, and then we do the model inference of different layers, different branches, and then do the prediction. And then we gather the next window of samples. So that's the normal sequential CPU way of execution. But on FPGA, because everything is run in parallel, we can do the sensor data acquisition at the same time as we do the inference of the model inference. And even with the model inference, if we have parallel branches, for example, that's why I mentioned the feature fusion. If we have these parallel branches, you see they are independent from each other. They can be run in parallel. So that's why I have these two plots on the FPGA. So one is a serial and the parallel, even though everything is in parallel on FPGA, but the serial means the branches are run in serial, and the parallel means the branches are run in parallel. So you can see with FPGA is way faster, and we can have way faster analysis. So maybe for daily activities, we don't need this fast, but for certain high performance sports, for example, I have another paper I forgot to put in here with the pressure sensor. So for example, soccer, I had the paper, I put the pressure sensor on the surface of the soccer shoe. We try to detect the motion of the ball kicking, and the ball kicking lasts only 10 milliseconds, for example. Then we need to have more than 100 hertz. We even need to go to almost to 800 hertz to sample that pressure sensor data, because if you have 10 millisecond contact time, 100 hertz will give you 1 point for that contact. But if you want the curve, we need multiple of that sampling rate. Yeah. So with this, it will allow such studies. So that's why we have these high performance infrastructures, high performance embedded devices. Okay, so that was everything that I wanted to present. I hope I hope it's something is new to you. And these are the overview again. And I want to plug in our call for paper for the East Week, which is in a little bit over a month from now on. Yeah, we welcome any submission related with wearable computing, and hope to see you in Melbourne. Thank you very much.
Okay, thank you, Bo. Thanks for presenting this large body of very impressive work. And also thank you for queuing our paper. I'd like to open the podium to questions. Feel free, you can just unmute your mic, or you could raise your hand. So I had Oishi. Please go ahead.
Yeah, thank you for your talk. It was really interesting because we're actually working with IMU sensors for smart home applications, but we're kind of getting stuck on that step of how to like extract the features or understand what's relevant to movement recognition. So I was just wondering, like, maybe if you had any suggestions for things I can read up on to understand that a bit better. Because I know you had a sensor fusion approach, but yeah, if you could explain a bit more how that worked, and maybe if I can get some ideas from there.
Okay, I don't really have the details in my slides, but so for example, I understand that your question is how to if there are existing models for IMU, basically, right?
Yeah.
Yeah. So if you want to curate features, then you use the frequency analysis and Fourier transform. But if you want to use deep learning, there are several models. So temporal convolution, maybe if you look into this, here. So there are these models that people can quite popular for IMU data.
Okay.
So CNN, of course, so temporal CNN. There's a new one. It's called the Tiny HAR. It's a transformer plus CNN. So they first reduce the dimension with the transformer. They first reduce the dimension with the CNN, and then they put into a transformer. So it is this transformer.
Okay.
They have GitHub, so you can directly use their code, or you can have a look at this tasked paper. Yeah, there's a list of different architectures that you can directly use.
Mm-hmm. Okay, thank you.
Welcome.
Holly?
Hi, thank you so much for the talk. I just wanted to make a comment about the League of Legends tests that you did. I think it would be really funny and interesting if we saw how Faker performed in terms of his eye movement, because we know that he constantly switches between looking at different players' perspectives. And I think that would be an interesting measure to see if there are more teamwork-oriented players, if their eye movement increases, and that if that could be detected in this particular test that you did, and if that's something you've already measured. Do you happen to have the results?
Yeah, exactly. So we did have some finding. So this experiment was run with two teams. One is an amateur team, and one is a professional team. So professional is like 0.5 of the EU server. We happen to have one of the team in the university. So we found out that the professional team, they stare dead in the dead center of the screen all the time. They don't need to look at so because their peripheral vision is enough for them to see the nuances in the map or mini map or anything. But the amateurs, they look all over the place, and like they move at the mini map and they look at the abilities, the build trees and everything. So that was something quite interesting for us to see. I think but there was, we didn't include that in the paper was because there was something already existing. Like there was already a paper. There was a IEEE conference on esports, I believe. So there was already a paper in this direction. So it was quite interesting to see for us. Yeah.
That's very interesting. Thank you. Maybe we can connect more and talk more about this paper another time.
Yeah, sure. Yeah.
Appreciate the talk. Thank you.
Thank you. Thank you for the question.
Any other question? So I have a question on the FPGA side of things. So I understand, from a timing perspective, be able to integrate sensing, inferencing on the single platform will be quite efficient. But if you look at the ability to parallelize, I mean, you can still, if you think about using conventional approach where you have external sensors and you can still kind of pipelining, you can get a buffer of data and start inferencing and so on, right? So pipelining opportunity still exists. But the other side is my understanding that PGA tend to be quite power consuming. Would that become a barrier for deployment on embedded systems?
Yeah, so thank you. That was a good question. So it was a good comment too. So of course, the pipelining, we can have the different sensor buffers and the inference in parallel on different threads, for example. But the actual FPGA compared with these microprocessors, their power consumption is surprisingly on a similar level. Because if you want to have, you can have very low power microprocessors, very low power CPUs, but they cannot do much. That's the problem. If you want high performance multi-core, they tend to add up like dramatically the power consumption. And another point, if so, I actually have I had during my own PhD, I had the FPGA system was even an old one that runs on batteries, so, wearables. So people always say I was crazy that I have an FPGA in a wearable with a battery. But the truth is, it was a very old processing node. It consumes like 100 milliwatt. And if you look at the embedded processors, they're also something like 100 milliwatt, maybe. I think Tinsy. No, Tinsy is smaller than that. But but Tinsy cannot also Tinsy cannot do too much with it. Yeah. But I think in the overall chain, FPGA is more in the overall value chain. FPGA is more like a stepping stone because eventually, for a large company, they can deploy everything on a chip. And also FPGA, it's when you look at the FPGA, it's less about that chip. It's more about the accelerator model. It's the accelerator, the Verilog, the VHDL module. So that module that can be moved to a separate accelerator chip, for example. And with the other, everything else moved to a CPU. So it's but it's just during research, the FPGA seems to be the most flexible way and with a little compromise. So that's why we have the FPGA in the wearable. So yeah. So another reason was we want to have these so the pipelining, we want to have these different studies of different sensors of different size of machine learning models. But once you start to engineer with the pipelining, the sampling rate will be affected. Doesn't matter how careful we are. So if we have, for example, if we have 2 threads for acquiring sensor data, But if we add another thread, the sampling rate of every other sensor, they will be affected, because that's how sequential implementation works. And the machine learning models, they implicitly assume a sampling rate. So once you change that sampling rate in the reality, then the actual pattern will fall into a different node in the machine learning model. Then it will no longer be the same as their older data, for example. Yeah. Hope
That makes sense.
I mean, it's
I think the
more like a
barrier.
discussion. Yeah, there's
Yeah,
no
there's
clear
also
yeah,
like
there's no clear
it's
answer, but it was more like a discussion. Yeah.
yeah. So just a very high level question you have. Oh, Dylan, please go ahead.
Oh, that's okay. You can go ahead. I'll jump in after if that works.
Okay. Yeah, like you work with a variety of sensors for HAR and plural of machine learning model. So as a veteran of UBCOM and ESWIC, where do you think the field is going? Like we're looking at more integrated solution, more sophisticated model, or this problem has been bitten so hard for decades by researcher and time to move on. What's your sense?
I wouldn't say I'm a veteran. I'm just starting to. I think this is like my like the title of my presentation. I think it will be a converging with the vision and language domain. Because there is so much implicit knowledge in that vision and language domain. What we need is reliable links between the sensors to either of these domains. So either language to sensor or motion to sensors. So there seems to already some, for example, the IMU poser or other transpose or IMU pose reconstruction. But of course, this is like this is a way that we can have a single context embedded space. And for us, our next project following Vision Sense is so we already have the project green lighted, is cross domain joint representations. So we will still have heterogeneous machine learning models, but they shall be trained in such a way that they join together, for example, like a clip or the other contrastive learning methods, that they are aligned together during the training process, so that it's more interchangeable. So the problem of human activity is always this heterogeneity in the applications, in the sensor data, in the manufacturer, in the users. But I think it's impossible to have a single standard. But if we have certain models start to accumulate on different studies, different data sets, to have a large and growing joint representation, I think that's where we want to go. Yeah. And the bigger picture, I think people always keep trying to find the new modalities to detect new activities. That's also always an interesting new topic in ISWIC. Yeah. Or for example, maybe I give an example for my favorite one from the last year's ISWIC. Was or maybe 2 years ago. So it was so we have this smartwatch with optical sensor to detect your pulse, right? This PPG sensor. But the problem is people with prosthetic arm, they cannot use that function, but they still want to use the smartwatch. But they also have a pulse, but from somewhere else. So this work was essentially they have a device to measure the pulse from elsewhere of the body, and they deliver that graphics through a screen, and then under the position of that smartwatch on the prosthetic arm. So the arm is essentially delivering this digital pulsing signal, and then they can use the smartwatch like anyone else. So that was a really interesting thing. This yeah.
That's interesting. Dylan, you had a question earlier?
Yeah, maybe. I mean, I have a number of questions. Great talk. Lots of really exciting information. We do similar things from activity classification, more specifically gait to like pulling out gait metrics and things like that. So I have a number of questions, but I'll kind of just stick to maybe one specifically that jumps off a little bit of that. But I'm curious on your thoughts on sort of the potential integration of like a physics-based model in some of this as well, because I think a lot of it is in the AI and machine learning side of it, and there's a little bit of thought of integrating those two together, and how you think that might come into play, or if you think it's necessary.
Yeah, certainly. Thanks for the question. So this is a direction that we also look into. So from what I understand, there are two ways. One is the model itself is embedded with the physics formula or loss functions through the training process. Or another way is we have sufficient training data, and the model would learn implicitly the physical rules, or how you expect with the physical rule, how you expect the physical parameter will propagate through the system. I think that's actually would really help us to break down everything into objective elements. So for example, there are certain activities that involves if you project these activities into different aspects, for example, maybe walking, you know the horizontal trajectory and the latent trajectory. So it will certainly help. But I think the challenge in this wearable is that so in my bachelor, what I studied was navigation for ships or submarines through these IMUs. So that is very reliable because these IMUs are like huge, like a car-size IMUs. They have a huge proof mass, so the spinning of the gyroscope, they're very steady, so there is no loss from that trajectory to the acceleration. But the wearable ones, they are tiny silicons, and so it's really difficult to inverse that back to 3D trajectories. So if that is one of the physics aspects, if we want to do that, this is one of the challenge. But if we want to use other physics principles, there's always this lossy process in the way that the sensor is equipped on the human body, and the way human just moves unpredictably. And the sensor characteristic may have the saturation and hysteresis properties. So maybe a sensor, for example, a thermal sensor, maybe they are usually slower. And then if we use that to detect fast activities, then there will be a hysteresis, and then it will be a lossy process. So I think these are the challenges, but I think that's a really it is one of our written in our project proposal of the cross joint representation, that we want to align some of the dimensions with certain physical definitions. Yes, of course. So that's a really interesting direction. Yeah.
Yeah, it's a good point, and I appreciated you commented on like the pose joint doesn't necessarily equal acceleration because the sensor is in different places, which I think is a really important thing, because we don't, I've always found when we try to simulate some of that stuff, it never really looks the same, and that's a lot of that, right? Is if it's just a basic simulation like that, then yeah, it's not the same because you're not representing where that sensor actually is, and the physics that it's undergoing. So maybe just like last quick one. This maybe is a quick answer, but I liked also how you talked about the real data and the simulated data integrated into the training, and to me it makes sense that if we just had simulated data, I have a number of concerns about that, because we work with a lot of clinical populations, and it's really challenging to translate that to the clinical populations that don't really move like what we would expect. But then integrating it with, as you said, you had the real data and the simulated data, that was kind of the best model. So just super briefly on that, like what ratio would you think is best in that? Like how much real data should you have to supplement the simulated data?
That's a good question. We actually haven't really quantified the ratio. I think my students, they just put all of the simulated data together with the training real data. But yeah, that's the what you mentioned about this clinical population is something that we actually haven't considered. That's certainly it just got me thinking that we can add this in the simulation pipeline, like we can guide the post generation with the clinical tendency, like clinical biases, to have some data more realistic to the clinical way of moving. But I want to note another thing is that it's not necessarily the model are learning the way they move. It's possible that the model learns some just simple, signal filter characteristics through the simulated data. So these are maybe already be helpful for some real data that is outside the distribution of a normal population. Yeah.
Yeah, it's a good point. And I think, I mean, as we have more of these sensors, like we're generating much more of this data, like the real data, I would say. And I expect that hopefully creates that snowball effect of we have more real data, we can generate more synthetic data that has a better representation, and then this just snowballs, right? And hopefully reach that tipping point very soon. But yeah, thanks.
Thank you.
I
Thank
think
you.
From the results, you've shown that after you actually adjust the simulation parameters, like to the anthropometric parameters of the target, the simulation data works better, right? So I think there's still some kind of customization, like if you just simulate data from any body shape, and it may not work too well. Is that the case that you found in your experiments?
So this was so what was better was we added variations of the body shapes. It was better than a single body shape. So that was what we found out. Yeah.
But if the body shape is identical, or at least very close to the target subject, would you anticipate
yes, I see.
it will be the best, right?
Yeah, we didn't have the real information of our users, so that this could be a way to fine tune a model, for example. Maybe do I still have that slides in here? Delete that slides. We actually have a paper on a virtual try-on that we reconstruct the human body, the user's body through pictures. But yeah, so that's something we can connect to. Yeah.
Yeah. So I think the reason I mentioned that I feel like for clinical population, it's probably better to, like, for the data synthesis to actually have include the characteristic of the target population for that to work well.
Yeah.
All right, so I think we are quite over time already, but really appreciate the wonderful presentation and the questions. Before everyone goes, I just want to have a quick reminder that please fill out the SMAP. If you're SMAP trainee, please fill out the survey that Elsia sent a few weeks ago. Okay, so let's thank our speaker again. It's really nice.
Thank you very much for including
I hope
me
we
in
can
your
follow up with more discussion, because there are quite a bit of overlap.
Yes, definitely.
In work. Yeah.
Yes.
All right.
So, I was really surprised to see the chromosome was from you, because I knew that paper before I actually I saw you in UVCom. Yeah.
Okay, thanks. Yeah.
Right.
All right.
Okay.
Good night.
Then
And thanks everybody.
have a nice weekend, everyone.
Thanks.
Bye.
Thanks so much. See ya.
See you. Bye.